write this as sum and or difference of logarithm, which means we're expanding this logarithm using log property. So first, we're going to rewrite this as log base 5 square root of half power, because taking a entire thing half power, because square root is same thing as raising to half power, right? So like this. And then using log properties, we can bring this half to here and multiply. Okay, so next line, or next step, I'm going to write as half times log base 5 of x to the third power times t over 7. So now what we're going to do is we're going to expand this logarithm. So let me do that in the next line. So we need to keep this half here. Half is multiplying. And we're going to make a big parentheses. So we're multiplying half to whatever we're expanding here. Since first this is division, we can write two separate log. Log base 5 of numerator minus log base 5 denominator, like this. And next line, we're going to keep this, we can multiply this half later. We can distribute it later. So then let's look at this portion right here. This log base 5 has two things multiplied inside. So we can also separate this. We can also expand this by adding with two separate log. So log base 5 x to the third plus log base 5 t minus log base 5 7. Lastly, this 3 right here can come here to multiply. So we have 1/2 log base 3 times log base 5x plus log base 5t minus log base 5 7. And finally, we can expand this, if we can distribute this half to get 3 over 2 log base 5x plus 1 over 2 log base 5t minus 1 over 2 times log base 5 7. So this is the final answer where we expand this log. So remember, we start with one log, but our end we had 3 separate log, and these two are equivalent statements. They're equivalent. So we're expanding this log. That means that we can write this log first as about log base 2 of numerator, since it's dividing, and we subtract log base 2x cubed minus 10. And this one, the second part here, there's nothing we can do anymore to simplify. You might think that this cube can come here, but no, because cube is only applied to x. In order to bring up into the front to multiply, it has to apply to the entire inside of log. But that's not the case here. But for the first one, this one we can bring this 4 right here and multiply. So we get 4 times log base 2 x minus log base 2 x cubed minus 10. And we do want to keep parentheses here, because if we don't put parentheses here, it may seem like we're doing log x cubed minus 10. It's not so clear that 10, subtracting 10 is part of log if we don't write the parentheses here. Okay, so this is the final answer right here. Okay, we're expanding this log. First, we have to recognize that in log, this is entitled like this, we're multiplying x to the fourth and this thing right here, 3x minus 4 to the 9th power. So first, what we do is we can add them, log. If base is not written, 10 is implied, right? Make sure you remember that. We can add the second thing we're multiplying, log of 3x minus 4 to the 9th power. Then for each of these, we can bring 4 to here. For this one, I can multiply 4 here. I can multiply 9 here. Okay, so we have 4 times log x plus 9 times log Make sure to keep the parentheses. If you don't keep the parentheses, it just looks like log 3x minus 4. This seems like log 3x minus 4, right? So this is the final answer. In this problem, we're expressing this entire expression to single logarithm. So first thing we have to do is we have to bring this exponent, the 4 to the exponent. So 4 n to the 4th power, 3 4 to the n power, 12 to k power, 4 to the w. Okay, so let me write that. So I have log 3 to the n to the 4th power minus log base 3 m to the 3 to the 4th power plus log base 3. As you notice, they have the same base, right? We can only combine them. We can only condense to one single log when we have same base. W to the 4th power. And then we look at from left to right. So next here, they're subtracting, so we can combine into one log and put a division inside. So I have log base 3 of n to the 4 over m to the 3 over 4th power. So that's just from these two. And yeah, these two, we haven't combined them yet, so keep it like this. And next step, we're going to combine these two. They're adding, therefore, we're multiplying. Log base 3, we do n4 minus, n to the 4th times k12. So n4 k to the 12th power over m3 over 4 power. Plus, we haven't combined that last one yet, log base 3 w to the 4. Lastly, we need to multiply w4 inside of single log because our goal is to put in one log, right? So I have log base 3, I'm multiplying, and 4th k to the 12th power, w to the 4th over m3 over 4 power. So in this problem, we start with 4 different logs, but all same base. Only same base can be combined together. All these 4 logs, but we end up with one single log. So we're condensing this log in this problem. So first, we have to bring this number multiplied here to exponent here. And also this 1/4 to this exponent right here. So let me write that first. I have log base a, 2x squared minus 3x to the 2nd power, minus log base a, x plus 11 to the 1/4 power. Now they're same base, right? So we can combine into single log. Since they're subtracting, we can put it the division. So numerator is the right here, 2x squared minus 3x, entire thing square, over x plus 11 to the 1/4 power. So in this problem, we start with 2 separate log, but we end up with one single log. Solve the equation 2 to the 5 minus 2x power equals 1/4. So this is an exponential equation. And solving means we're solving for unknown variable or unknown variables will make this equation true. So there's many strategies we can take, but for this problem, what we can do is here we can leave it like this. If you can have a same base, so I'm going to rewrite this 1/4. Well, 1/4 is same as 1 to the 1 over 2 square, which is same thing as 2 to the negative 2 power. So I'm going to rewrite 1 over 4 as 2 raised to negative 2 power. Now that we have a same base, we can set the exponents equal to each other. Right? This must be equal, right? If these left and right are true. So we cannot always do this, but if you can make same base left and right, we want to make a same base in exponential equation problems. So then we know that 5 minus 2x equals negative 2. Now solve for x. Let me subtract 5 both sides. Negative 7. And x is negative 7 over negative 2, which is 7 over 2. So 7 over 2 is the answer. That means if I plug 7 over 2 here, I'll get 1 over 4. So this is the solution. solve the equation 3 raised to 3x minus 1 equals 9 raised to x minus 1. Solving means we want to find a known variable will make this equation true. In this case, this is an exponential equation. And if we cannot always do this, but if you can make the same base on the left and right, so we can write, instead of 9, I'm going to write 3 squared to x minus 1 power, which is same thing as 3x minus 1 equals 3. I'm distributing 2 to x and minus 1. So I get 3 raised to 2x minus 2. So then, since base is same, 3 raised to 3x minus 1 equals to 3 raised to 2x minus 1. That means that these must be equal to each other, right? So set those equal to each other. 3x minus 1 equals 2x minus 2. So for x, collect like terms. So I'm going to subtract 2x both sides. Then I get x, right? X minus 1 equals negative 2 if I subtract 2x both sides. Now I'm going to add 1 both sides. X equals negative 2 plus 1 gives me negative 1. So if I plug negative 1 here in both equations, I'll get the same. Left and right will be same. So negative 1 is the solution. Solve the equation 8 raised to the x plus 2 equals 16 raised to x plus 1. So in this case, we have an exponential equation, and we want to find x values that will make this equation true. So here, we see that right away 8 and 16 are the same base. But if we can make it the same base, we should. So here, 8 is actually the same thing as 2 to the third power. 2 to the third power to x plus 2 power equals 16 is the same thing as 2 to the fourth power, x plus 1 power. Then we can actually distribute 3 here, 4 here. Then we get 2, 3x plus 6 power equals 2 for x plus 4 power. Now that we have the same base, that means that this exponent must be equal to each other. So set them equal to each other and solve for x. 3x plus 6 equals 4x plus 4. So I'm going to, let's say, subtract 3x both sides, then I get 6 equals x plus 4. Subtract 4 both sides, x equals 2. So when x equals 2, the left and right are equal to each other. So x equals 2 is the solution. And we can always check our answer. 8 to the fourth power is the same thing as 16 to third power. Solve the equation log of 3x minus 2 minus log 2 equals log x plus 4. So this is a log equation, and when we're solving log, we always have to check our answer in the end. So don't forget that part. So first, for this problem, what we're going to try is we're going to try to combine this to single log first, so that we get log of 3x minus 2 over 2 equals log x plus 4, right side. Now here, we have log of something equal log of something. That means the inside must be equal to each other here, right? So we set inside equal to each other to solve for x. 3x minus 2 over 2 equals x plus 4. Now we're just solving for x. But again, one thing is that we need to check our answer in the end. Okay, so we'll do that. So but let's solve for x first. So first I'm going to multiply 2 both sides, and I get 3x minus 2 equals 2 times x plus 4, which gives me 3x minus 2 equals 2x plus 8. Let me subtract x both sides, then I get x minus 2 equals 8. Add 2 both sides, x equals 10. So is this a solution? What we need to do is we need to plug 10 here and here, and inside of log always has to be positive, right? So if I plug 10 here, I get 30 minus 2, which is 28. I get positive, that's fine. I can plug 10 here because it gives positive. But how about here? If I plug 10 here, I get 14, right? 10 plus 4 is 14. So it has to work for all the logs. Here, there's no x, so we don't have to worry about that. If it doesn't work in any of the one, even if it doesn't work in one log, that's not a solution. But in this case, the solution works, so x equals 10 is the answer. If 10 didn't work, if plugging 10 give us negative or 0 in any of the log in given equation, then that's not the solution. Solve the equation ln x squared equals ln 2x plus 3. Here, we already have ln of something equals ln of something. That means the inside must be equal to each other, right? So again, this is still a log problem, so we do have to check our solution in the end. So this is what we're solving for. So let's subtract 2x and 3 both sides, so we have a quadratic here. Here we can either use quadratic formula or we can factor. So we're going to factor here. We have x and x minus 3 and plus 1. So what we get is x equals 3, x equals negative 1. So those are the possible answers. But again, we do have to check both of these answers. Can I plug in all of this? So let's see 3 first. Can I plug 3 here? Yeah, because if I plug 3 here, I get 3 squared is positive. That's okay. How about here? 2 times 3 is 6, 6 plus 3 is 9, is positive. That's okay. Because inside of log, we can only plug positive numbers. Does plug negative 1 give us negative? Let's see. Negative 1 squared is 1, so that's okay. 2 times negative 1 plus 3 is 1, so negative 1 is also okay. So both of these answers are solutions to this problem. Solve the equation log base 2 of x minus 3 times x plus 1 equals 5. So this is still a log equation, so we need to check our answers in the end, check our solution in the end. So here what we need to do is we're going to rewrite it as exponential. So we can write this entire thing, log entire thing. So we know that rewriting exponential form, we know that 2 raised to 5th power gives me this inside. So we know that x minus 3 times x plus 1 is result of 2 raised to 5 power. So then let's multiply this out to solve for x. We get x squared plus x minus 3x minus 3 equals 2 to the 5th power is 32. So we get x squared minus 2x minus 3. Let's subtract 32 both sides like this. Equals 0. So x squared minus 2x minus 35 equals 0. So we have a new quadratic to solve here. So let's factor this. We get x times x equals 0. If it's not factorable, we can always use quadratic formula. Even if it's factorable, we can still use quadratic formula, right? So this is actually 5 and 7. It'll be negative 7 since it's negative 2x and plus. So x equals negative 5 and x equals 7 are the candidates for this answer. So let's see. If I plug negative 5 here, I get, let me do a different color. Let me try negative 5. We're checking our answer, okay? Checking. If I plug negative 5, I get log base 2 negative 8 times negative 4, which is positive number here, right? Positive number, negative times negative 5. So negative 5 is okay. How about 7? I get log base 2, 7 minus 4. 7 minus 3 is 4. So I get 4, log base 4 times 8, which is also okay, right? It's positive number. So 7 is also answer. So both of these answers are solutions. So we always have to check our answers for log equations, because inside of log, we cannot have a negative nor 0. Solve the equation log base 2 of x minus 3 minus log base of 2 x plus 1 equals 0. So here, what we're going to do first try is rewrite the left side condensed to 1 log. Log base 2 x minus 3 over x plus 1 equals 1. So then, the reason we do this is that we can rewrite this as exponential form, because we know that 2 raised to 1 power must give us this inside, right? So that means that x plus 3 over x, oops, sorry, not plus 3, x minus 3. X minus 3 over x plus 1 must equal to 2 by this logarithm equation. So using this, we're going to solve for x. So let's multiply x plus 1 both sides. Distribute 2, so I have x minus 3 equals 2x plus 2. Let me subtract x both sides to get like this. And subtract 2 both sides, and I get x equals -5. So then we have to check our answer. Can I plug -5 here and here? If it fails in one place, it's not a solution. We can see right here, we get -5 minus 3 is -8. Doesn't work. So this is not a solution. So in this problem, we don't have solution, no solution. Okay, so identifying the no solution is also important, right? We did solve this problem, and solution of this problem is just no solution. And it also fails here, right? But again, it needs to fail only one place to be not part of the answer. So -5 is not a solution. So no solution for this problem. Solve the equation e to the x equals 17. So in this case, what we can do is we can take natural log of both sides of the equation. So we have natural log of e to the x equals 17. Natural log of 17. And here, using the log property, we can bring x here. Then we have x times ln of e equals ln of 17. And we know that ln of e equals 1. So we have x equals ln of 17. And ln of 17 is just a number. It's a decimal number. And this decimal number we cannot calculate without a calculator. Okay, so this is the answer. And remember, ln of 7 is just a number, so we treat it like a number. Why is ln of e equals 1? Well, ln is same as log base e of e. So this is asking e, what do I need to raise e to get e? It's just 1, because e raised to 1 is e, right? That's why ln, which is same as ln e, ln of e, or log base e of e, is equals to 1. Solve the equation 1 over 2 ln of 2x plus 5 equals 7. So here, first we're going to multiply 2 both sides, so we can isolate this. So I have ln of 2x plus 5 equals 14. And then what we're going to do is we're going to rewrite this in terms of log base e, 2x plus 5 equals 14. So that we can rewrite this as an exponential form. Well, this tells us that e raised to 14 must give me this, right? So 2x plus 5 must equal to e to the 14th power. And keep that in mind, e to the 14th is just a number. E is a number. E is just a number, like 2.7 something, unending decimal. So this is just a number, so we treat it like a number. So here we want to solve for x, so just isolate x. Subtract 5 both sides, we get ex, 2 to the x, sorry, equals e to the 14 minus 5. X equals e to the 14 minus 5 over 2. Okay, now the question is, can we plug that in here? Okay, so let's see. If I plug to x there, I get 2 times e to the 14 minus 5 over 2 plus 5. Cancels out. E to the 14 minus 5 plus 5 cancels out. I get e to the 14. And e to the 14 is a positive number, because e itself is positive. And if I raise that to even bit, the 14th power, it is end result is also positive. So this is okay. So this is the solution. And we can leave it like this. Again, this will be a very long ending decimal number, but this is an exact number. E to the 14 is a number minus 5 over 2. If we try to write this in a decimal number, it has to be an estimate, because we have to round it. Solve the equation 5 raised to 2x plus 8 equals 22. So in this case, this is the exponential equation, and we cannot make the same base both sides. Right? There's no way we can rewrite 22 so it be raised to 5 power. So what we need to do is we're going to take natural log both sides of the equation. Okay, so what we're doing is take the natural log of both sides of the equation. So like this. Like this. Right, natural log both sides. So then this allows us to bring this here. So we have 2x plus 8. Now this parenthesis is important. Make sure to keep this parentheses. times ln of 5 equals ln of 22. If you don't write this parenthesis here, it seems like you're only multiplying 8 to ln 5. Remember, ln 5 and ln 22 is just a number. So we treat it like a number. So we are solving for x, so let's just multiply this out here. Distribute ln 5 here. So I have ln 5 times 2x plus 8 times ln 5 equals ln 22, or natural log 22, if I should say that. Again, our goal is to solve for x right here. So we're going to isolate this term and everything else will be other side of the equation. So I'm going to subtract this both sides. So I have ln, I'll keep messing that up, ln 5 times 2x, and this cannot be ln 10x. This is as simple as we can write it. ln 5 is a number. This is not ln 10x. We cannot multiply these two numbers here. Furthermore, equals ln 22 minus 8 ln 5. We want to solve for x, so I'm going to divide by 5, ln 5, sorry. Well, 2x equals ln 22 minus 8 ln 5 over ln, keep messing that up, ln 5. We want to solve for x, so we're going to also divide by 2 as well. So let me write the final answer here. Final answer is x equals to natural log of 22 minus 8 times natural log of 5 over 2 times natural log of 5. This is the final answer. And if you type this in a calculator, it will give you a decimal number. Right? But this is the exact answer. Decimal number, we have to round it. Okay. But again, each of these is a number. Number. And we cannot simplify this to, we cannot multiply this here. That's not allowed. We cannot also multiply this here. This is as simple as we can write it. Solve the equation 2x power equals 7, 3x minus 1. Here we have exponential equation and we cannot rewrite this to same base. So what we do is we take log both sides. In this case, I'm going to take natural log. And you can take just regular log as well, log. Either one's fine. Any of them will give us same answer. So then what this allows us to do is we can bring x from here and this exponent right here. So let's multiply that. We have x times ln of 2 equals 3x minus 1. This parenthesis is important, ln of 7. If you don't write the parenthesis here, it seems like you're only multiplying negative 1 to ln 7, right? And this is important because we need to distribute this ln 7 here. So I have x times ln of 2 equals 3x ln of 7 minus ln of 7. Our goal is to solve for x, right? Here's x, here's x. That means that all the terms with x should be in the one side of the equation. So I'm going to actually subtract this both sides. So I have x ln of 2 minus 3x ln of 7 equals negative ln 7. Remember, natural log of number is just a number. So we treat it like a number. So here I'm actually going to factor x out. So I have x, parentheses, and remaining ones, let me write different color, ln of 2 minus 3 ln 7 equals negative ln 7. And we're to divide this by both sides to get final answer is x. So x equals negative ln 7 divided by that entire parenthesis. ln 2 minus 3 ln 7. So this is the final answer for this problem. Again, if you type this in a calculator, it will give you a decimal number. Okay, but this is the exact answer. And again, this is number. ln 7 is a number, ln 2 is a number, ln 7 is a number. So we treat it like a number. The population of a small town is modeled by the equation P equals 1000 e to the 0.3 t power, where t is measured in years. In approximately how many years, rounded to decimal place, would the town's population reach 10,000? So here, let's set up the problem. And the reason I put 2 decimal places here is so that we can kind of get a sense on how many years that will be. Okay. But as long as we need to be able to solve the problem and set the answer to exact answer, we should be okay. So first, we get population equation. Whatever the population is followed by this model, 1000 times e to the 0.3 to t. This is asking how many years. This is asking for t value. What is the t value when the population is 10,000? So we set population to 10,000 equals 1000 e to the 0.3 t. And we want to find the time, the year that will make this is true. So this is essentially the exponential equation problem. So let's divide by 1000 both sides. Then I get 10, right, equals e to the 0.3 t. So then at this point, I can take natural log both sides, like this. Then I get ln of 10 equals, I can bring this to the front here, 0.3 t times e. Oops, sorry, I forgot the ln. ln of e. And ln of e is 1. So essentially what we have left here, let me write this here, is ln of 10 equals 0.3 t. So what is t? T equals ln of 10, which is a number, over 0.3. So this is how many years it would take for it to reach population of 10,000. So this is absolutely acceptable answer. Or if you want to see roughly how many years, because this doesn't give us a sense how many years this will be, right? So if you put this in a calculator, you get around 7.675, around the 2 decimal place, so it will be 7.68 about years. Again, the 2 decimal places we're only doing to kind of get a sense, but this is the exact answer, and this is absolutely acceptable answer. Definitely okay. A radioactive material decays according to the function a of t equals a naught e raised to negative 0.0212 t, where a naught, this is how we say it, a to 0 or a to naught, is the initial amount present, and a, this on the left side, is the amount present at the time in t years. Okay, so initial amount, and this is after some time has passed, or even at the in the beginning. Then we just plug 0 for time, right? Assume that the scientist has a sample of 150 grams of radioactive material, which is the initial amount. So let's look at first problem. What is the decay rate? So rate can be figured out by this number right here. So what we get is negative 0.0212, right? Well, rate we don't usually write in percent. So we multiply 100 to get percent. We get negative 2, move 2 decimals here, right? 2.12%. That's the decay rate. Okay, negative 2.12% is the decay rate. So the second part, how much radioactive material is left after 10 years? So we're finding a of t at 10 years. Then we just plug 10 to t. Again, this is a of naught, right? The initial amount. So we have 150 e to the negative 0.0212, 10 years, 10, which is 150 e to the, multiplying 10 was only 1 decimal, right? So we have negative 0.212. So again, this is acceptable answer. Okay. But if you put this in a calculator, we give a roughly about 1.106518 grams. Okay. So this is the exact amount, but I know this doesn't give us this number set. So if we type this in a calculator, give 106.518. Part C is asking the half-life of the radioactive material. So half-life means, as the word says, how long does it take for it to have half of the amount? So we know that the equation was modeled by initial amount, e to the negative 0.0212t. And I know that we know the A naught is 150 for this problem, right? But this half-life, we don't actually need to know the initial amount. We're asking, okay, this is the initial amount. How long will it take to reduce to the half of the initial amount? So that's how we put half of A of naught. So you can put 150 here. Whatever you number put for A naught, it will be the same procedure because they'll end up canceling out. So we want to isolate this. So I'm going to divide by A naught both sides. So essentially, it just becomes exponential equation problem with just half like this. So then we're solving for t here. Okay, so how we can solve for t? We take natural log both sides like this. So we're going to bring this to the front right here. Then I have negative 0.0212t ln of e, which is just 1 anyway, but let me write for now, equals ln of half. So let me bring all this here. I get negative 0.212t equals, because ln of e is 1, ln of half. We want to solve for t, divide by that number. So this is the acceptable answer. Okay. So you may be confused that, oh, how can I divide by a negative number? Am I going to get a negative time, negative years? No, it is possible for natural log or log to give us a negative number as a result. Inside, we cannot have negative or 0. But output, ln of half is actually a negative number. Okay? So this is the acceptable answer. But if we type this in a calculator, we'll get about 3270. So this is about 32.7 years for the initial amount to decrease the half of it, its initial. Which means if we start at 150, it would take this amount of years to reduce to 75 grams. So let's sketch the graph. We know the initial amount was 150, right? So it starts at 150, right? Let me write the equation first. So we have 150 e to negative 0.0212t. And because it's negative, we know this is decay. If it were to be positive, it would be increasing, but it's negative, so it's decreasing. And we also know this has horizontal asymptote of 0. Exponential equation, right? This cannot be 0 or less than 0 or negative, right? We start with 150 grams and it decreased by a certain percent every year. But we cannot reach the negative amount, nor the exact 0 amount, right? We're always taking percentage of positive amount, which will always give us a positive amount. Even if it's very small, it will be always greater than 0. That's why we have a horizontal asymptote here. So how does the graph look like? So it starts at 150, initial amount. And that's when this is t, right? X-axis is t, this is p, y-axis is p. If I plug 0 here, right? For example, p of 0 is 150 times e to the 0, because 0 times anything is 0. E to the 0, anything to 0 power is 1, so p to the 0 is 150, which checks out with our initial amount. So it actually intersects here. And we know the exponential graph decreasing looks something like this. It has this curved shape decreasing like this. And decrease forever. And essentially, it's going to be so small that it's going to be very close to 0. But again, it does not arrive to 0. It does not get to 0. It gets very close, decrease forever. Let me draw that better. So this is the shape of this graph, which shows that forever decreasing, but never below x-axis in context of this problem, and also the exponential function context.